If you remember back when we studied Hess's law last year, we were looking at how we were able to add up a series of reactions to give us the net equation that we were interested in finding the delta H of. So in this case, we have two simple reactions, and we need to add them up to give us this reaction. The rules of Hess's law says that whatever we do to the reaction, we must also do to the delta H value. When you're doing a Hess's law problem, always work from the reaction that you're interested in finding the delta H of. So here, we need to find solid carbon as a reactant, and only reaction 1 gives us that. It gives us other species as well, but we're not interested in those at the moment, just getting this carbon as a reactant. So reaction 1 will give us that value, and its delta H value remains unchanged. If we look, we need to get half a mole of oxygen, but we have oxygen in both reactions, so let's move on from that and we'll come back. Here, the reaction that we're looking for needs to have carbon monoxide as a product, and we have carbon monoxide, but it is as a reactant. So we will need to flip this reaction in order to get our carbon monoxide on the right-hand side. When we do that, we also need to change the sign or flip the sign of the delta H value. When we write these reactions out, taking the first reaction as it is written and flipping the second one, we can see that the CO2s cancel, which is good because we don't want them. We see that we have half a mole of O2 over here and a mole of O2, so that would leave us with half a mole of O2, which is what we're looking for, and we have our carbon monoxide as a product. Taking the reaction delta H values and adding them up for the change in their signs and the values, we get a negative 110.5 kilojoules, which is the heat of reaction for this reaction that we were looking for. Hess's law, quite powerful law that we'll use throughout the year, says that if a reaction is carried out in a series of steps, then the delta H for that overall reaction will be the sum of the enthalpy changes, or delta H values, for the individual steps. Let's look at another delta H problem. So here we're looking at that idea that when you reverse your reaction, you're going to reverse your delta H, and if you need to multiply your reaction by some coefficient, you'll need to multiply that delta H value. So here we're looking at adding up these three reactions to give us this reaction here that we do not have the delta H of. So working from this reaction, we can see that the first reaction we would probably use is number 2, because number 2 gives us carbon solid as a reactant. But notice we need 2 moles of carbon solid, so we would need to multiply reaction 2 by 2. Moving across, we need to find a mole of hydrogen gas as a reactant. The only reaction that gives us hydrogen gas is reaction number 3, and it gives us a mole of hydrogen gas exactly as we need. So we're going to leave reaction number 3 alone. So we have doubled number 2, we leave number 3 alone. Now we need to find C2H2 as a product. Here we have it as a reactant. So we have a mole of it. All we need to do is flip this reaction in order to get our reactant as a product. So if we rewrite all of these reactions, flipping them, doubling them, and then adding them up, you will see that we end up with our C2H2 as a product, our 2 moles of carbon, and our mole of hydrogen as a reactant, and all of the other species that we don't want in our net equation have nicely canceled out. We then can take and do to the math what we have done to the reactions. We flip the sign of reaction 1, we double reaction 2, and we leave reaction 3 alone, making sure that we pay attention to the thermodynamic signs. At that point, when we add them up, we get a positive 226.8 kilojoules, which would be the delta H value that we would be able to place in the fourth reaction's value.